just few more lectures, and when we're the problem set is due tomorrow, and then the date for midterm I already announced is going to be the last Friday of the quarter. I think that's June 7th, and we'll have it during the class time, 4:15 to 2 hours. Yeah. Are you previous commitment, then we can schedule it next week, but we'd prefer if you can take it on this day. So today I want to finish up on solar thermal, and then also talk about thermophotovoltaics that we briefly talked about when we were discussing the limits of solar energy conversion. So I described you that we could achieve up to 85% efficiency if we heat up the cell to a very high temperature above 2000 Kelvin. So that is the field of thermophotovoltaics. I'll talk about how that is done, what kind of materials are needed to achieve that efficiency. And then today, and this is a theme that will continue in the next lecture, is that we're going to talk about what are the new ideas going on, what is the research community, or what are the new startups, or at least the way both the research community as well as some of the startups, what they are aiming at, what are some of the new ideas happening in the field. So both in terms of cell design, in terms of materials, and so on. So today I'll mostly focus on the new ideas in the crystalline semiconductors. Okay, so just to wrap up on solar thermal, we talked about this thing, the solar field. So solar thermal has basically three components. You can divide it into consisting of three different modules. One is the solar field, which takes this sunlight and concentrates into the heat receiving element, and that is of different forms. We saw that it could be a form of these parabolic throws, it could be a form of these solar towers, or it could be a form of these solar disks. The second component is usually the storage, especially if you want to achieve the real benefit of having this thermal energy, converting into a thermal energy. That is, you can store it for a few hours, and typically you have two of these tanks. One is hot and one is cold, and you run the fluid from the hot tank through your solar field. So the fluid from the hot tank, it runs through the solar field, and it gets collected in the fluid from the cold tank runs through the solar field, and it gets collected in this hot tank. And the more capacity you want, and the more storage capacity in terms of the delay between your sunlight and your power supply, the more is the capacity of the tank you need. And the third part really is the part which is the generation part, which takes this hot fluid, uses it to heat the steam, and converts it into electricity. And this is very similar to what you would get in a coal plant or any other plant which uses steam to convert it into electricity. Some of these plants, at least this is not a topic we'll discuss in this class, but one of the real innovations that's happening in this space is they, instead of converting the steam back to water, they use a supersaturated steam. So even when it expands, it remains in the steam form. So you avoid, you gain some efficiency points over there. But at the same time, if you run the turbine with steam, it corrodes more rapidly. But anyway, that's something you might want to study in a mechanical engineering class. So we were discussing these three kind of systems. One was a throw, which focuses all the light on this receiver, The other was the tower, which has multiple of these mirrors, and they all shine the light onto this receiver. And the other, which we also saw in concentrated photovoltaic systems, is this disk, which concentrates it again to a receiver. So, just to check whether you remember what we discussed last time. So, which one of these achieves the highest concentration? The disk, right? So TRAW typically has a concentration of 30 to 40. The tower can go up to 1000. Typically it's around 700, 800. The disk can in fact go up to 3000 because it's a 2D concentrator. It uses and it has a much smaller focal length, so it can achieve very high concentration. As a result of that, it has the highest efficiency as well. So these disk-based solar thermal systems can achieve efficiencies well above 20%, right? And they don't use any semiconductors, so it's cheap, it's efficient. So in places where you can do it, where you have good direct incident sunlight, it makes a lot of sense to do this solar thermal, right? And then the next thing I talked about was that receiver which is receiving all your heat. So this is typically called heat collecting element, or HCE. And we were discussing the properties that this heat collecting element should have. And I told you that in an ideal world, if you could, if you had the hand of God, and you could design a material which would have which could have any possible absorptivity or emissivity spectrum, you would design it to be the absorptivity or the emissivity to have this step function kind of a profile, where it absorbs everything in this part of the spectrum where sun is. So sun, you can treat it equivalent to a black body at 6000 Kelvin. So it absorbs everything in this region, while it emits out everything it absorbs everything in this region, while it has zero absorptivity or zero emittivity in this region, which is corresponding to the temperature it gets heated up to. So in this case, let's say if I'm putting this in that solar tower, that typically heats up to a temperature of 700 centigrade. So I want it essentially to have zero emissivity in this range. So it should have this perfect emissivity or perfect absorptivity. Remember, these things are, absorptivity and emissivity are just the same thing. They are reciprocal of each other. So sometimes I say absorptivity, sometimes I say emissivity, but they are the same thing. So if something is a good absorber, it's also a good emitter of light. So it should have, it should have essentially zero absorptivity or emissivity in this range. So when you look at it, our human eye is sensitive to this range, right? This is where the visible spectrum is. So when you look at one of these heat collecting elements, since it has perfect absorptivity in the visible spectrum, it appears black to our eye. Okay. Now, so let me ask you something, right? So if I increase the temperature of this heat collecting element, so if I vary the temperature of essentially my heat collecting element, my wavelength, or the wavelength at which the step function occurs, that's called the cutoff wavelength, right? So if I change the temperature, that wavelength needs to change as well, right? So if I increase the temperature, should that wavelength increase or decrease? If I increase the temperature at which my receiver heats up to, should that wavelength, that cutoff wavelength of that step function, should that increase or decrease? Decrease. Okay, so the reason being? Okay, so remember we talked about, Ben said it correctly, so we talked about this black body spectrum. So as the temperature increases, the spectrum has a blue shift, right? So it moves. Remember Wien's displacement law, it says the maximum wavelength is essentially inversely proportional to the temperature. So the hotter your black body gets, it emits light at lower and lower wavelengths, right? So if I increase the temperature of my receiver, the spectrum which my receiver is emitting is going to shift towards the left, and correspondingly the wavelength at which my receiver cuts off, at which the step function cuts off, has to decrease as well, right? So now this brings me another headache. It gives me a lot of another engineering problem to solve. That is, I'll design these receivers for different kind of systems. I'll design one receiver for the Stroh system, which heats up only till 400. I'll design one for my solar tower, which heats up to 700. I might design one for my disk, which heats up to 900. So for each of them, I have to design this. I have to do this optical design depending upon what is the temperature of my receiver, right? And in general, as Ben just said, that if you increase your temperature, this cutoff wavelength of my step function has to reduce. So if I am at a temperature of 720 Kelvin, my cutoff wavelength is let's say 2.2 micron. If I'm going to go to higher temperature, my cutoff wavelength, let's say if I'm temperature of my disk, which has a temperature of 1000 Kelvin, so I'll have a cutoff wavelength which is somewhere around 1.5 micron in that case, right? So this is all well said and done in theory, that you want something which has a step function in terms of its spectral response, but it's very hard to achieve practically. So I'll show you some ways, and also the most common ways in which people try to do this. And bear that in mind, because when we talk about thermophotovoltaics, you'll see the same idea, that you design these systems which have a spectral response which is like a step function. And it's used in multiple of these both solar and optical systems. So a figure of merit to essentially quantify this absorber. So it needs to have this perfect absorptivity in the solar part of the spectrum and zero absorptivity in the other part of the spectrum. So figure of merit is essentially to calculate this absorptivity. So we calculate how much it absorbs, and we calculate it according to the spectrum from the sun. So we take the energy distribution of the sun, you average it over all the wavelengths in which the solar spectrum lies, and you calculate the absorptivity in the range of the solar spectrum. And then you calculate its emittance, so in the range in which it acts as a black body, so it heats up to, let's say, 720 Kelvin. So in the wavelengths around that range, you see how much does it emit, and you want to minimize this term. So you want to minimize the emissivity in the range of the temperature at which it heats up to. At the same time, you want to maximize this, maximize its absorptivity in the range at which your solar spectrum lies. So a figure of merit is essentially to take the multiplication of these terms. So take the absorption in the range of the solar spectrum, and then take 1 minus the emissivity in the range of temperature in which it acts like a black body.